Good afternoon, everybody, and welcome back to the second webinar of INSPIRE, the International School on Modern Physics and Research. The next webinar is held by Anna Grassellino. Anna Grassellino is the director of the Superconducting Quantum Materials and Systems Center at Fermilab. Among her research fields, she pioneered the studies on superconducting radio frequency cavities for next-generation particle accelerators. She is the recipient of many awards, among these the Presidential Early Career Award for Scientists and Engineers. As usual, you can write your questions in the chat, and at the end, we will answer to a few of them. Dr. Grassellino, the floor is yours.
Thank you very much, Susanna, for the invitation. I'm very excited. I would be more excited to be in Italy, actually, with you, but Zoom works. Let me try to share my... Oh, can you actually see my slides already, or...?
At the moment, no. Just a second. Now, yes.
Perfect. Thank you very much. Okay, so today I will be talking about SRF technology. As you heard from Susanna, this is the technology I've been working on for many years, starting as a student. And I will explain a little bit what's special about SRF technology and give a glimpse on the research that has been taking place throughout the years here at Fermilab, where this technology has been employed for building cutting-edge, state-of-the-art particle accelerators, but actually as we moved this technology also to be key to enable new applications as detectors and in quantum information science. I put the acknowledgements up front, the founding acknowledgement. This work is supported by the Department of Energy and various programs from the General Accelerator Research and Development Program of the High Energy Physics portfolio, to the Basic Energy Science LCLS2 project, to the new Department of Energy National Quantum Information Science Research Centers. Okay, so this is the outline. I'll be just giving a brief introduction on what this SRF technology is. SRF stands for Superconducting Radio Frequency Technology, how these cavities are employed for current and future accelerators. I think you heard a wonderful talk right before me from Dr. Lucio Rossi, who has told you everything about cutting-edge, exciting particle accelerators. And now, in fact, the superconducting technologies are at the core of the most modern particle accelerators. And then I will dive into how SRF cavities really, by moving them towards the quantum regime, which means really far away from where we use them for particle accelerators, they can become building blocks for quantum computers and for quantum sensors. Okay, so how are particle accelerators in modern machines? Typically, you heard most likely from Lucio how superconducting magnets are critical to keep particles on trajectories when accelerators are circular. But an element that is key is the element that gives the acceleration, that the accelerator is linear or that is circular. Those cavities are always needed. Now, those cavities can be made out of copper, or they can be made out of niobium, so or other superconducting materials. SRF really means cavities that imprint an acceleration to a beam that goes through them. So here you can see a cartoon where basically you can imagine a surfer that goes on the crest of the wave. So the beam is synchronized with the electric fields in the cavity. And in particular, for superconducting RF technology, what it means is that the walls of this cavity are made of a particular material, which is a superconductor. In the most common that is employed in this technology is niobium, which has a critical temperature of 9.2 Kelvin. So it means that if we cool them down below this temperature, they pretty much lose all electrical resistivity in DC. But if we are in radio frequency condition, they still have a little bit of residual resistivity that still, though, makes them very, very, very efficient. Over billions of cycles, this very large electric field are generated. And so what it really means is that we are exciting an electromagnetic wave inside, and you can think that in the typical regimes in which a particle accelerator operates, we have about 10 to the 25 photons stored inside the cavity. I introduced this quantity to you because you'll see later that when we actually employ these cavities, not for accelerator application, but for detectors, or especially for quantum information science, we dial down how many photons we store in this cavity from 10 to the 25 all the way down to one single photon inside these cavities. So what makes SRF so special? Really, these superconducting cavities because of this parameter that I introduced, so the surface resistance that is very small. It's in the order of nano-ohms. So the quality factors of these resonators are in the order of 10 to the 11. So this makes them the most efficient engineered oscillators that exist. So here we put things in context. You can see Galileo's pendulum, the best pendulum clock, quartz clocks, IQ, copper cavities are in the range of, let's say, 10 to the 5. The best superconducting qubits demonstrated in 2013 approximately in the order of 10 to the 8. Our niobium cavities that we have demonstrated at Fermilab exceed 10 to the 11. So really the only thing that beats us is atomic clocks. It's nature. So what makes them so high efficiency? Again, so this is how they work. So you have a structure that can be like this, elliptical, or it can be also different shape depending on the type of beam you want to accelerate. But really, if you zoom in, this is a 3 millimeter thick niobium wall. On one side, the wall of this cavities will be cooled by liquid helium. Temperatures below, typically for niobium in accelerators, we go below 2 Kelvin. On the other side, inside the cavity is where the radio frequency fields, the electromagnetic wave is. And then if you further zoom in at this surface, you can see here you have niobium, and then you have a niobium pentoxide of about 5 nanometers. The RF currents, when you're in the superconducting state, flow in the first 100 nanometers. So really, all the action takes place in the first 100 nanometers. And really, what is really critical is the nanostructure in these first 100 nanometers that will go and determine if this oscillator, if this resonator has a quality factor of 10 to the 7 or 10 to the 12. So the characterization and the nanoengineering of the surface layer is crucial to performance. That's one of the first main messages I want to pass on the research I've been doing for many years, both for accelerator application and for quantum application, for detector application, where we need to push the envelope, where we need to really employ all our brain and resources is in engineering the surface and understanding scientifically how the surface behaves under these particular conditions, and make it better to allow for these accelerators and for detectors to really enable a next generation of experiments, of physics experiments. So material science and superconducting characterization tools are key, have been essential throughout the years for us to push this technology forward. We employ a variety and the most advanced techniques. I will give a glimpse of that, but here you can see some pictures like TM, SEM, SIMS, secondary ion mass spectroscopy, electron beam scattering diffraction, or even more exotic techniques like muon spin rotation. We really have explored all possible techniques to really go hand in hand with the device performance and the material surface characterization. What is really important, of course, to go with that is the fact that this make it state of the art. So here you can see some of the treatments and the infrastructure that really is critical for this technology to perform at best, from treating it in class 10 clean rooms to doing special furnace treatments in high vacuum, high temperature furnaces, some sophisticated chemical treatments to treat this delicate surface in the best possible way, and then of course frequency tuning and much more. I had a little video that shows quickly how an accelerator is built. So this is an example of, so those cavities are for the LCLS2 project. This is one of the light sources that we have been building here in the United States at Stanford. So you saw the assembly of this string and clean room. So each of these objects is a cavity that gains, so as the beam goes through, gains about 16 million volts of acceleration. And the key thing is that actually we have been making it so that they have much higher quality factor than previously demonstrated. And this way we will be able to operate this light source rather than in pulsed mode in what's called CW mode, in continuous wave, which gives us very important opportunities in terms of, so something like 1 million pulses per second versus the previous light source was 100 pulses per second as slack. Like this very important beam structure gives us more opportunity in terms of the physics reach. Here you can see all of this going from clean room to assembly to on a truck and shipped to SLAC. So you may be familiar with some of these. The European XFEL is a similar accelerator. In Europe, it's about 1,000 cavities. LCLS2 SLAC is about 400. Now we are building an upgrade with an extra 300 cavities. So again, we have been able to demonstrate construction of now at this point of this type of accelerators with superconducting cavities routinely with very high performance. Here you can see the specifications demonstrated that XFEL larger than Q10 to 10 over kilometers of accelerators in the tunnel. And with LCLS2, we actually demonstrated we tripled almost the performance, going with Qs of larger than 2.7 10 to 10 operationally in the tunnel at 2 Kelvin and 16 million volts per meter. So what is the factor of merit? What our research has been focusing on over the years has been really pushing two main parameters. One factor of merit, of course, is how much acceleration can I imprint through each of these cavities. If I can imprint 20 megavolts, 40 megavolts versus 100 megavolts, of course, it makes a huge difference in terms of length of this tunnel, which means also in terms of overall cost of an accelerator. So for a linear accelerator, this is particularly important, for example, where an accelerator like an ILC would be 30 kilometers if the cavities operate at 30 megawatts per meter. But if it can operate 3 times that, then you can shorten it 3 times. Of course, it's not that simple. There is a lot of other considerations that go that need to be made. But anyway, here there is some examples of how both the quality factor, the efficiency of this cavity, and the accelerating gradient really can make a huge difference in terms of cost of an accelerator. And that's why we push very hard on that. And then the quality factor really is critical in terms of cost as well. Here's an example of how, so this is the cryogenic infrastructure that goes with an accelerator such as the LCLS2 SLAC. So for building LCLS2, 2 cryo plants for 8 kilowatts at 4 Kelvin, at 2 Kelvin, I believe, have been required. And so you can see clearly that, you know, it goes directly with the quality factor. So if we can push the quality factor from 1.5 directed to 3.5, we cut the refrigeration in 3. So these are the two main parameters of merit. So SRF has been having several decades of evolution. Many years ago, the limitation was at 3-4 megawatts per meter in terms of what's called multipacting. So it was a resonance of condition of electrons in the cavity. By changing the shape, this was overcome. Thermal breakdown was the next limitation. This was overcome with the invention of using niobium of higher quality, of higher purity. So triple R, what we call triple R, residual resistivity ratio larger than 300. Field emission was the next limitation, which was overcome by the invention of the high pressure water rinsing. So where we really treat these cavities in class 10 clean room with this particular treatment that really removes any surface contaminants. And then 25 megawatts per meter was the next limitation, which was overcome by the invention of what's called mild bake. So baking these cavities at very low temperature. We were able to then reach accelerating gradient up to 40 megawatts per meter. I was able, as a postdoc here, to witness the invention of nitrogen doping. This was during my research as a postdoc at Fermilab, which tripled the performance of these cavities. You can see the huge jump in quality factor. This was by doping with nitrogen. And we built actually the next accelerator with this. So LCLS2 was built with the invention of doping these cavities with some interstitial nitrogen. And then we also witnessed the combined effect of having nitrogen in a thin layer to actually give the benefit of both Q and accelerating gradient. So we continue today to make do a lot of research to enabling future efficient high energy machines. So in principle, SRF cavities could perform up to 100 megawatts per meter or above. There is no fundamental limitations, and it's all research that revolves around, again, this nanostructure in the first 100 nanometers. So new materials, new dopants, new thin layer structure. So we work hand in hand, theorists and experimentalists, to really understand how these superconductors behave under this radio frequency field, and how to nano-engineer the surface to really enable these cavities to reach the next frontier. So advances in SRF cavity performance improve the feasibility of building new accelerators with unprecedented reach into unexplored scientific frontier. And here you can see on a map really a variety of accelerators around the world that are being constructed or that are planned, including the Future Circular Collider, for example, at CERN. In the case of SCCEE, for example, it heavily relies on SRF technology. And actually high quality factor SRF technology. And the PIP2 accelerator that we're building at Fermilab as a driver for our flagship neutrino program. Okay, so this concludes the part on the accelerators. I hope I gave you a glimpse of the exciting results we've had throughout the years, but also the exciting prospects for the future. One of the things that we did as we were working on these cavities was starting to explore really using them for quantum information science, for quantum application. And so you can see here a nice picture, a 650 megahertz cavity like the one that we use for PIP2, or this is about the size of what would be used, for example, for potentially an FCCEE. 1.3 gigahertz was used, for example, for XFEL, and then all the way down to a tiny cavity, 9 gigahertz, for example, here. So all these variety of cavities can be used for example, for quantum information science. So we started to explore how these cavities behave at very low temperature and at very low photon counts. I mentioned earlier 10 to the 25 photons. Now, if we want to go to the quantum regime, it really means manipulating single photon level inside these resonators. And so it really means we need to dial down all the way the power to control single photons, but also we have to dial down all the way the temperature to make sure that there is no thermal photons. So the first studies we started to do were 1.4 Kelvin, and then we actually switched to what's called a dilution refrigerator that actually can allow to go to temperature like 6 millikelvin, where really there is absolutely no thermal photons for this particular frequency range. So this is a part of the research that we have been doing. So as I showed you earlier, the quality factor as a function of the accelerator field, it's critical to determine what the physics reach of this object is for both accelerators and quantum application. And so in accelerator application, I showed you a midfield, for example, for light sources, is very important to push this quality factor. For high gradient, we need to push in this direction. For quantum, the question is, what can we achieve in terms of quality factor when the Q goes to very, very low fields? So dialing down all the way to 1 photon. And that is a not straightforward and a very challenging problem, because the physics of the surface in these regimes of low temperature and low power is actually very different than in the saturated regime when there is many billions of photons. So one of the first studies we did was really observing this and studying this quality factor decrease when we started to dial. So counterintuitively, actually, as you dial down the power, as you put less photons in the cavity, actually the quality factor decreases. So at about 1.4 Kelvin, we observed though this saturation at about 310 to 10. We did study as a function of different surface condition what this decrease in quality factor low field was. And so again, I don't want to go too much in detail, but really one of the key messages here is that while for the accelerators, what applications, what really matters is really the quality of the niobium, the interstitial structure of the niobium. For quantum application, that is less important. And what really seems to matter is the so-called two-level system losses that reside in amorphous substrates. So as we dial down the power, as we dial down the temperature, the mechanism that dominate dissipation in the structure is really in the amorphous oxides. And so the pentoxide of the niobium becomes really one of the challenges that we need to overcome. And so we did a lot of research, and you'll see more about this later, on how we actually pushed to world record quality factor by eliminating this surface pentoxide. So let me switch on using these cavities for detectors. One of the things that we thought would be very important to do is, can we use these cavities to discover if there is or exclude the existence of new light particles, such as axions or dark photons, and we can test two hypotheses. So by using either by listening to the universe, so doing sort of like dark matter type of experiments, or by doing light shine through wall type of experiments. So here is the scheme, for example. So light shine through wall, we have an emitter, a cavity which emits, so that it contains a lot of photons, and then photons remain contained in the cavity, but dark photons, the dark counterpart of the photon that we want to prove or disprove the existence of, is very weakly it's an hypothesized particle that very weakly interacts with matter, and so it does not remain contained inside the walls and will cross the walls and will materialize as a photon then in the receiver. So this is a search for a mediator, this dark photon. Or we can also search for dark photon, for example, dark matter, by just utilizing a cavity as a receiver and listening to the universe. There were some previous searches using, for example, copper cavities, utilizing this type of schemes. And you can see here that the sensitivity of these searches really is a byproduct of the quality factors of the emitter and the receiver cavity. And so by having, in this case, it's less than 10 to 5 for a copper cavity. So that's where we started. We thought, okay, with SRF, we are larger than 10 to 10. We can really offer several orders of magnitude improvement in sensitivity. And so we did run our first experiment of this dark photon search, where we used the two cavities, 1.3 gigahertz, one powered up with a lot of photons inside and one silent, almost in the quantum regime. And here's a picture of the experiment. So you can see it's a very, so it was nice because we could basically utilize a lot of the expertise and tools that we had in-house. It is not simple experiment. I mean, it seems kind of simple, but it's not. So you have now two cavities that have a quality factor of 10 to 10, which means like millihertz bandwidth or below. And you have to really synchronize them on exactly the same frequency. So there are some sophisticated tuner and piezoelectric mechanisms that ensure that those cavities really stay exactly on the same frequency, to ensure that, if dark photons are there, we can say, yes, we detect or we exclude the presence of this particle. Here's some nice pictures of the experiment, people at work. And so we did a first round that actually, and this is some preliminary results of this experiment, where we actually excluded the existence of dark photons by many orders of magnitude compared to previous similar experiments. So this was very promising. One of the things that we want to do now, this experiment was conducted at 1.4 Kelvin. And then one of the next steps is really to take it in the full quantum regime, where there will be absolutely no thermal photons. And so we will be able to extend this sensitivity further. And also using quantum tricks, we will be able to again, be even more sensitive. So now, so far I described this type of experiments being at 1.4 Kelvin, which means in around thousands of photons. I want to show you some of the first work taking cavities in the true quantum regime. So this is what I was mentioning earlier. Cavities at around 1 or 2 Kelvin, we have been able to have very good quality factors of the order of several 10 to 10s or even above 10 to the 11. But as you take them to the true quantum regime, you observe this interesting drop of more than an order of magnitude. And this is what we call the two-level systems dominated regime, where these losses in the oxide really dominate and cause this drop in Q, which is really undesired. I mean, again, for quantum application, for detector application, we would like to keep the quality factors of these resonators as high as possible. So we did an experiment where this cavity had niobium and niobium pentoxide on top, and then we actually dissolved the pentoxide in situ via some special heat treatments. And we'd really observed, by comparing, a jump in performance of more than an order of magnitude. And so I just want to mention that for the quantum state of the art, really the best resonators were in the order of 1 millisecond. And we were able to demonstrate 2 seconds of coherence, what we call quantum coherence. So if this cavity is sitting in the quantum regime, really hosting a handful of photons, how efficiently can it store these photons? And we have demonstrated 2 seconds. So this is really the world best quantum memory ever demonstrated. Okay, let's switch to qubits. So what does it mean to actually use these cavities in the quantum regime? why can they be an enabling technology for quantum? So qubits, first of all, what are qubits? So they're basic unit of quantum information. We need two-level quantum mechanical system, and we need to utilize a very special quantum mechanical principle, which is two states of the quantum system that can be prepared also in any superposition. And we also utilize entanglement between the qubits. So by utilizing this very powerful quantum mechanics principle, superposition and entanglement, a qubit can be much more powerful than a classical bit that is what enables information processing in our classical computers. Now, what are the main challenges? So qubits really are the main building blocks of a quantum computer. Quantum computers do exist today, IBM, Google, Rigetti Computing. There are various companies around the world that have demonstrated quantum processors doing some sort of computations that already outperform classical computations. Again, they're very special type of computations. But what is the limitation today of these primordial processors is that the quantum coherence, what I've been describing so far, really how well can a device store quantum information without losing this information. So in the case of a cavity, as I described, if I have this one photon that is bouncing inside this cavity as a perfect mirror, if it leaves 1 millisecond or it leaves 2 seconds, this will make a huge difference in terms of the type of algorithms that I'll be able to run through my processor. Because if it's 1 nanosecond versus 1 millisecond versus 1 second, I have to kind of restart my computation, of course, way less frequently. And so really the quantum coherence, how well I can maintain superposition of the states inside my device long enough to perform a large number of gate operations, is the critical quantity we are trying to push. There are various architectures today for building quantum computers. Of course, what we focus on, because of our expertise in superconductivity, is the superconducting qubit architecture. In the case of IBM or Google or Rigetti, what this means is a silicon substrate with on top a Josephson junction and some resonators that really very much resemble what we do in the 3D world, in this 3D cavities world. There are also 3D architectures, for example, pioneered by Yale, where the cavity, rather than the transmon qubit, sorry, I'm going very fast, those are complex concepts, but I'm trying to simplify as much as possible. Again, for superconducting qubits, there is really two main components. One is what's called the transmon qubit, which is an LC circuit with a Josephson junction. This is really what's needed to introduce kind of a non-linearity. So you need a device that can really allow to have one photon, let's say, in a superposition of two well-defined energy levels, 0 and 1. So if I have a device that gives me equally spaced energy levels, I cannot achieve that. I need something that has anharmonicity. And so that's what the transmon qubit does. And then the resonator is what's used to read out and control the transmon qubit. So this is how a 2D classical processor look like. In a 3D architecture, actually, the resonator, the qubit, the transmon qubit goes inside the 3D resonator. So in 2D, the resonator is a serpentine. In 3D, you have just what we're familiar with, like a 3D pillbox, a cavity. So this is kind of what we're doing. We're really pursuing this 3D architecture where a transmon qubit gives non-linearity to our system, and then we are able to store a single photon and make this overall device act as a 3D qubit. So the main challenge is really improving the coherence of both key components and also scaling up to large combined system. So in the 3D architecture, on a cartoon level, how we encode a qubit inside the cavity. Here, there's some example. So you see one of our cavities, and then you see a transmon qubit inside. That really means we insert one of this chip inside this cavity. And we can call the ground state, for example, with no photons as state 0, or one single photons as state 1. This is called Fock states. Or we can call, for example, an even number of photons as state 0 and an odd number as state 1. The transmon qubit is used in this particular architecture for state creation and quantum operation. So why we do all of this? Again, because with the knowledge that we have of how to make those resonators the best in the world by many orders of magnitude compared to what others have been doing, really we can bring a great advantage to the world of quantum in terms of having the best 3D quantum processor in terms of coherence, and therefore in terms of potentially algorithms that can be run through these devices. And here is an explanation also of why this architecture can be very powerful. In the qubit approach that I just described, we use 2 states. In qubit approach, one can use even more than 2 energy levels for quantum computing. And so here's an example of how this works. These qubits may allow for faster scale up and have also what's called a hole-to-hole connectivity, which can open further options for quantum algorithms and simulations. So now why SRF is the unique platform for qubit implementation is because in order to store and manipulate many multi-photon states, they must live long enough. So this coherence concept is key. So let's say that even 1 photon is absorbed, the state is destroyed. So let's take an example. Each photon in SRF cavities lives, let's say, 1 second. Then the state of 1,000 photons leaves tau divided by 1,000. That's 1 millisecond, which is still long enough. So currently, other 2D and 3D platforms that are not SRF do not have this enough coherence to take this qubit approach beyond several photon states. Single photons will live way less than that. With our SRF platform, we are targeted to very ambitiously control more than 10,000 photons per mode, equivalent, for example, to 13 qubits. So in a nutshell, very high level, with the 1 9-cell cavity we use for accelerators, if we are successful what we're trying to do with 1 cavity and 1 qubit, 1 transmon qubit, we are able potentially to even turn this whole object into a 100+ qubit equivalent processor. So let me just conclude the next 5 minutes by telling you a little bit on, so we started all of this research really with some kind of internal to Fermilab projects, internal seed funding. But then in 2019, really, there was a large investment from the Department of Energy that created the 5 national quantum information science research centers, $600 million over 5 years. Fermilab won one of the 5 national quantum centers. So we are, at this point, actually more than 22 partner institutions, and actually we have reached more than 300 collaborators. What the goal of these centers is really to, of course, at Fermilab, we have a lot of expertise, as I just described, but really those centers bring together national labs, academia, and industry to tackle together, and bringing all the different expertise that the different sectors bring to really produce state-of-the-art, beyond the state-of-the-art quantum computer and quantum sensors. So here's an example of some of the infrastructure and the different expertise that we bring together. As an example, we work hand in hand with one of the leading industry in the quantum field, which is Rigetti Computing, and they help us turn these structures into an actual processor, and we help them turning their processor into better processor by bringing our expertise in superconductivity and radio frequency superconductivity that again employs very similar materials, just in a 2-dimensional layout. We actually have, as a partner, that we're very proud to be working actually with the Italian Institute of Nuclear Physics. We have more than a dozen PIs from across the country, from Padova, from Rome, from Gran Sasso, that work with us in improving the performance and understanding the performance of these qubits. One of the key measurements we'll be doing is actually taking some of these qubits that we're making together with Rigetti Computing and moving them across the various partners and then all the way to the underground Gran Sasso to study the effect, for example, of environmental radioactivity on these qubits and much more. And we have also partnership with NIST, for example. So we bring together expertise in making qubits, in making devices, in testing devices, and in the application of these devices for computing and for quantum sensing. So this is kind of the chain. We go from material discovery to make better devices, integrate them into system, making new revolutionary platform for quantum computing and quantum sensing, and really demonstrating quantum advantage for high energy physics, for condensed matter physics, for industry cases. So really the power of these centers is to really bring together all the experts in these various steps of the chain. I don't think I have time to go through all, but so I can just go through these slides to just show you. So in materials, of course, we work hand in hand with the experts in the fabrication clean rooms and the material characterization experts to really, we take devices, we dissect them, we study them, then we understand what the limitations are at the nanoscopic scale, and then we inform the clean rooms how to make better devices. And so really, this is an example how we work hand in hand with the industry to make better processors. We use our cavities, as I mentioned, as a 3D QPU platform, but we also use them as very sensitive tools to characterize materials and understand, let's say, how dissipative is silicon, how dissipative is sapphire, and really what are the best materials to be employed to push the performance of these quantum devices. So this is the work ongoing in terms of the 3D integration. This is the experiment where we'll be moving cavities and qubits around the world, from Fermilab to Rigetti, Colorado and NIST, and all the way underground at Gran Sasso to really so this is the largest sort of coordinated benchmarking study that has ever been done in terms of superconducting qubits around the world. And also, I just want to show, because we are an energy physics laboratory, we want to take advantage of the large facilities that we have and the expertise, for example, in cryogenics. We want to build a very large dilution refrigerator, the largest ever built, that can host thousands of qubits, with the goal of really hosting our first quantum computer prototype here at Fermilab. This is our roadmap on how we will be pushing beyond the performance of the current systems by really improving the quality of these devices, but also pushing the system size. So number of qubits and quality of qubits. And again, the very same devices that we're using, that we'll be using for computing, also turn out to be exquisite detectors, in the quantum regime, where, in these very sensitive environments, we'll be able to detect an axion, perhaps, or exclude with the best possible sensitivity the presence of an axion or dark photons or other hidden set of particles. And we're doing a lot of research in advancements, for example, materials that can withstand very large magnetic fields in the quantum regime to really have the best of all. Okay, in conclusion, those are very exciting times for SRF Technologies. We're going from accelerators to quantum. World-leading coherence of our SRF resonators is really the key parameters that can enable new accelerators, but also quantum computer of record performance and capabilities. The expertise and methodology that we have developed in the SRF field are directly relevant and instrumental to advancing the field of quantum computing. High-Q cavities, RF design and engineering, superconducting material characterization, thin film deposition, scale-up and integration, cryogenics. We are really excited that we're employing all our expertise for this new exciting field, and we look forward to bring to life the first SRF quantum computer here from in the next few years. Thank you.
Thank you, Dr. Grassellino, for this very interesting overview. Maybe we have time just for one or two questions. Let me know. The first one in case is, can you please repeat the technique to detect dark photon that you show in the first part of your talk?
Yes, absolutely. Let me go back to those slides. Okay, so here is, maybe we can just start from this. So this is a light shine through wall type of experiment. So we have a cavity that is, so the photon, so the hypothesis is if dark photons exist, photons convert into dark photon. Photons interact with matter, so they stay confined inside the cavities, but dark photons do interact very weakly or do not interact, and so they can actually cross the cavity walls and reach a second cavity, which will be our detecting cavity, the receiver cavity. So let's say these two cavities here, emitter and receiver. So the emitter serves this purpose. I power it up with a lot of photons, about, like, say, 10 to 25 photons. So lots of photons produces also a lot of dark photons. Sorry, and then the dark photons reach the second cavity, reconvert into photons. The second cavity it's not powered, it's silent. So it's a detector in as silent condition as possible. So if I start picking up photons in my second cavity, then the only way that these photons could have gotten through this cavity was through this dark photon mediator. So that's the kind of the basic principle of a light shine through wall experiment. this cavity is silent. I don't detect anything. I detect only noise. So of course the limit of the sensitivity of the experiment is how silent can this cavity be. And so, as I mentioned earlier, if I do the experiment at 1.4 Kelvin, that's the equivalent thermal noise of 1.4 Kelvin. If I do it in the quantum regime, there's pretty much nothing at all. It's really empty. So this is how the experiment looked like, right? So this cavity is powered at about, as I said, 40 megawatts per meter, so 10 to the 25 photon. This one absolutely silent. So this whole thing gets dipped into a dewar in the ground and cooled down with liquid helium to about 1.4 Kelvin. And so then these cavities become superconducting. They have a quality factor very high, of the order of 10 to 10. So this means basically that you have a bandwidth of like millihertz, and you need to synchronize, because it's light shine through wall, they have to be exactly on the same frequency to be able to detect this potential dark photon. And so this cavity up here has, as you can see here, this tuner mechanism that really ensures that these two cavities are exactly synchronized on the same frequency. So that's more or less the concept here.
Okay, thank you. The last question is, has a quantum computer prototype ever been realized, or in case at which stage we are in the realization of a quantum computer?
Yes, absolutely. So there are quantum computers that exist, quantum processors, even of various architectures, actually. If we focus on the superconducting architecture, which is the most kind of advanced, IBM, Rigetti, and Google, they all offer superconducting processors that actually, for example, our researchers in the center, they access and they run various simulations. They study what kind of computation, what kind of applications can be enabled by this processor. So a couple of years ago, there was this demonstration of quantum supremacy by Google with I believe a 53 qubit processor, and they demonstrated what does quantum supremacy mean. It means that they ran some particular computation that on a supercomputer, actually the most powerful supercomputer existing, like Summit at Oak Ridge, would have taken thousands, if not millions of years. The processor at Google the quantum processor took about a few minutes. So that's really what quantum supremacy, the first quantum supremacy demonstration means. Again, was it an application of, impactful for society? No, it was more like an academic exercise. But it does signal the entering of an era where those objects, so again, quantum processor is not meant to replace classical processors. It will not be superior for all type of applications. For some type of application, it can offer exponential speed up type of advantage. And so for that particular calculation that was run, this was kind of demonstrated. So that's the stage where we are. Still, the limitation is, again, that these computers are very noisy. These qubits are very noisy. When we say this coherence is 20, 40 microseconds in these devices, it really means that after 20 microseconds, if I'm trying to run an algorithm, my qubit gives me an error. So at that point, either I have to reroute my information through redundant qubits or before it's lost. And so that means you need millions of qubits to do useful calculations, or I have to improve the quality of these fundamental building blocks. So that's the concept I try to explain here, why, for example, SRF can be really impactful, because if it can leave seconds versus microseconds, then really we will be able to do calculations which are much more powerful and have much more depth.
Okay, so thank you so much, Dr. Grassellino. We were so glad to have you here virtually with us. And okay, thank you also to our spectators, and talk to you soon. Bye-bye.
Thank you very much. Thank you. Bye-bye.